Welcome to another session of stoichiometry. This time we're going to deal with stoichiometry involving volume. As you can see, the first example here has to do with what is called a volume-to-volume problem. This is very similar to a mole-to-mole problem. It only involves one step. And if you look here, we're going to use the same method that we did when we were finding mole-to-mole problems. When you read a question, what I'd like you to do is label the given with the letter A, the unknown or whatever you're looking for, label it with the letter B, and we can solve this in one step. The only difference is that instead of the units being in moles, they're going to be in volume. Usually it's going to be in liters. So you're going to be given the volume of the given, or A, and you're going to multiply by B over A. This is the same as the mole ratio, except we'll just call it the volume ratio, but it's obtained the same way. It's found by getting the coefficients from a balanced equation. So as always, make sure before you start that the equation is balanced, and once balanced, you can perform this problem. Once you multiply by B over A, you will get the answer, and that will be the volume of B, or the unknown. So we can solve these in one step. Let's take a look at an example. Here they're asking you how many liters of CO2 will be produced by burning completely 5 liters of C2H6. So the given here is 5 liters of C2H6. So I'm going to label him with the letter A. This is my given. And we are being asked to find CO2, so we're going to go ahead and label this as B, and they want it in liters. It's a volume-to-volume problem because the given is in liters, volume, and they're asking us to find the unknown in liters, which is also volume. So the way we set this up is we get the volume of the given, or volume of A being C2H6. So that's given here, 5 liters of C2H6. Then we're going to multiply by B over A, or the volume ratio in this case. The coefficient of B is 4. The coefficient of A is 2. We can reduce that. You're basically just multiplying by 2. Okay, 4 over 2 does reduce to 2 over 1, or just 2. And when you do the math and you multiply by 2, you end up getting the answer, which will be the volume of the unknown, in this case CO2. And that's going to give us 10 liters of CO2. And I rounded it to 3 significant digits based on the question. Okay? So here's a sample problem for you. Try this one. We will talk about STP in the next problem. We don't need to know about that in this particular problem, but you're going to notice that this equation is balanced and it's a volume-to-volume problem. Go ahead, pause the video, work it out, and then we will do this together. Okay, so I'm assuming you worked out this practice problem. So the question asks, how many liters of oxygen? So here's oxygen over here. This is going to be B. We're looking for liters. They do tell us that we have 4.5 liters of butane. That's this guy all the way over here. That's our given. 4.5 liters. Notice it's another volume-to-volume problem. They do tell us that butane is used in cigarette lighters. Okay? So this is a combustion reaction that you are looking at here. And in order to solve this, we're going to get the volume of the given of A. A happens to be butane. We're going to multiply by the mole ratio, which in this, B over A is 13 over 2. And when you do the math here, you're going to get 29.25. Now we're going to round this to 2 significant digits, so it's going to end up being 29, and it's going to be liters, because it's volume, of B, okay? And B is going to be of oxygen. And that will be the answer to our problem. Okay? Now, not all problems are volume to volume. You might have what is called a volume to mass. And I'm going to teach you how to do these under what is called STP conditions. In this lesson, we will only learn how to do volume stoichiometric problems at STP. So what does that mean? STP is an acronym. It stands for standard temperature and pressure. You see, at STP, the temperature is 0 degrees Celsius, which is 273 Kelvin. And the pressure is the pressure at sea level, which is basically 1 atmosphere or 1 atm. But what's important here is that there's a conversion factor. You see at the bottom here, 1 mole of any gas occupies a volume of 22.4 liters. So this is the key new step to the problem, that we need to use that conversion factor. When we're doing a volume to mass, the first thing you always need to do in a stoichiometric problem is always try to convert to moles so we can cross this bridge. If you're given volume and it's at STP, what you're going to do is, using this conversion factor, is you're going to end up dividing by 22.4. Now, when we do a problem, I'll set it up so you can see that when you go from volume to moles at STP, by using the conversion factor, you divide by 22.4, and that gets you to moles. And then the rest, it's similar to a mass-to-mass problem. You multiply by the mole ratio, that gets you to moles of B, or the unknown. And then to go from moles to grams, you multiply by the molar mass of the unknown, or B. So here, we have a practice problem. It says, how many grams of water? Let's pause here for a minute. Water is going to be what we're looking for, and they want grams. That's mass. They're giving us 1.24 liters of H2O. The fact it says STP, you know we're going to need to use that conversion factor. So here's the given. We got 1.24 liters. And it's reacting with oxygen. That part is not important for the math. So according to the flow chart, we need to go from the volume of the given into moles of the given. Now the flow chart says we're going to divide by 22.4. I'm going to set it up so that you guys can see how this is done. 1.24 liters. You see, you can use dimensional analysis and use a conversion factor. Okay, this will be one easy way to do it. See, for every 1 mole, there are 22.4 liters at STP. Using dimensional analysis will allow us to divide here. That's basically what I'm doing, dividing by 22.4, and you're going to get this number. Now, there's more numbers. We only need at the end 3 significant digits, so that's good enough. This is moles of the given. Now we're ready to cross the bridge. The bridge is the mole ratio. The mole ratio happens to be B over A is 2 over 2. So in this problem, the number does not change. It's still 0.005. Let me fix that up. That looks a little messy. So it's 0.055357. But it's no longer moles of A. It's now moles of B. B happens to be water. So we got to do one last step. So we multiply by the mole ratio. We got moles of B. And now what we're going to do is go from moles to mass of B, which is in grams. B is water. And according to the flowchart, you're going to multiply by the molar mass of B. And remember, never use coefficients to find molar mass. So the molar mass of water can be obtained very easily. There's 2 hydrogens in water, 1 oxygen. Hydrogen's 1.01. Oxygen is 16. So you got, let me fix this up. I apologize. So you got 2.02 here, plus 16. You got 18.02 as your molar mass of water. So according to the flow chart, if you get the moles of B, which is 0.055357, B happens to be water, and you multiply by the molar mass, which is 18.02, and that'll be grams per mole, the moles will cancel, okay? And let's do this in a different color here. Let's go, you're going to get 0.9975. If we round this to 3 significant digits, it rounds to 0.998 grams of water. And that will be our answer here to this. This happens to be a volume to mass problem. Okay? Now, let's do the opposite. Let's do a mass to volume problem. This time, you're starting with grams. Now, this shouldn't surprise you. This is pretty simple. The first thing you always do, assuming the equation's already balanced, is change grams to moles by dividing by the molar mass of A or the given. This is again at STP. When you're going from mass to volume, you change to moles as your first step so that you can cross the bridge. Once you're in moles, you multiply by the mole ratio, which is B over A, and that will give you the moles of the unknown or moles of B. Now, they don't want the answer in grams nor moles. They want it in volume. Usually, they'll ask you for liters. So to go from moles to volume, as long as it's at STP, which these problems will be, the conversion factor will allow you to multiply this time. This time, to go from moles to volume, you're going to end up multiplying by 22.4. Now, I will show you the setup when we do a practice problem so you can see how that last step is the only thing that's new and you're multiplying by 22.4. So here's a sample problem. They want to know the volume of hydrogen gas. Here's hydrogen gas. Let's put B. They want volume. So let's put here volume question mark. They're letting us know it's at STP. That's a reminder that you're going to use the 22.4 liter conversion factor. As you continue reading the problem, notice you have 6.54 grams of zinc and it's reacting with hydrochloric acid. The key here is zinc. Zinc is your given. And you have 6.54 grams. So you're in mass and you want to go to volume. It's a mass to volume problem and it's at STP. First thing we must do is we must change the mass of the given into moles. And if you recall, all we got to do here is we're going to divide by the molar mass of the given. So you're going to get 6.54 grams. And if you go to the periodic table, okay, most periodic tables have zinc as 65.39 grams per mole. We're going to divide here, and that's going to give you 0.1000 moles of A, or zinc. Now, the mole ratio here, notice it's B over A is just 1 over 1. The mole ratio is 1 over 1. So the number does not change. However, you're no longer moles of A. You're now moles of B, which is hydrogen. So once you multiply by the mole ratio, you get moles of B, and here is the new step. To go from moles of the unknown into volume, as long as you're at STP, which we are, you're going to just end up multiplying by 22.4. Now, I'm going to set this up using dimensional analysis so you can see how units cancel. You see, there are 22.4 liters for every 1 mole at STP. So when you do the math here, notice using dimensional analysis, you're going to end up multiplying and you end up getting 2.24. I'm already rounding it to 3 significant digits, and it's liters of hydrogen, and that is your final answer. Okay? Now let's try one more. So here we have a sample problem for you to try. First, figure out, is this volume moles? I'm sorry, volume mass or mass volume? I'm going to give you a few minutes. Pause the video, and then we'll come back and we'll check it together. Okay, so I'm assuming you are back. Notice the equation is already balanced. They're asking us for liters of oxygen. So oxygen is our unknown, or our B. So we're looking for volume. The given here is 10.5 grams of water. So let's call water the A here, the given. And we got 10.5 grams. This is a mass to volume problem. You are given A in grams, and you're being asked to find B, oxygen, in liters. So the first thing you need to do is we need to change the grams of A into moles. Now, if you recall, water, and I'll do it quickly here, remember to ignore coefficients. Very important when you're finding molar mass. So I need to find the molar mass of water, which is 18.02 grams per mole. So the first step is to get the grams of the given divided by the molar mass of the given. The given is water. Okay? And when we do that, we're going to change this to moles of A. That ends up being 0.58266. There's more numbers. I think that's plenty. That's moles of water. Now our next step is to, now that we're in moles of A, we're going to multiply by the mole ratio. Well, if you look here, B, the coefficient is a 1, and A is a 2. So the mole ratio is 1 over 2. That simply means you're going to divide that number by 2, and you're going to get 0.291343, and that's going to be moles of oxygen. Okay? But we don't want moles of oxygen. We want the volume. We want liters of oxygen. So here I will set up, using dimensional analysis, there are 22.4 liters for every 1 mole. According to the flow chart, it just says you're multiplying by 22.4, but if you look at my setup, that's what I'm doing. I'm multiplying by 22.4, and let's go ahead and do that in round 2, 3 significant digits. You end up getting 6.53 liters of oxygen. Okay? So a lot of times, these 3 types of stoichiometric problems, volume, 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 mass, and mass volume, okay, are taught in the gas unit, okay, but it is part of stoichiometry. You learned in this lesson how to do volume to mass and mass volume at STP. There is another condition where it's not at STP, but in order to do that, you need to use, it's a little bit more complicated because you need to use the ideal gas law. So in this lesson, we are only learning how to do volume mass problems when they are under STP conditions. Okay? And that'll conclude today's lesson.